Welcome to chapter 4 of this course. We start a new chapter. That's always a good point to look back what we have done already. So chapter 1 was on things that we didn't want to do in the introductory course. For example, proving the full law of large numbers or proving the existence of independent random variables. Then chapter 2 was more a methodological chapter where we got to know the tool of characteristic functions and the tool of weak convergence. And chapter 3 was then more a model chapter. So we looked at these Markov chain models, which can model certain real-world phenomena. And we developed a theory for that type of models. Now, chapter 4 is again more a chapter on tools and on methods. It's on conditional expectations, and we're going to need these tools in chapter 5 when we deal again with models, and there we are going to deal with martingales. So chapter 4 has roughly 3 parts. The first part, 4.1, 4.2, is purely measure theoretic. It's on the Radon-Nikodym theorem. Sections 4.3 up to 4.5 are really the core. This defines conditional expectations, gives the existence theorem, and lists properties. And then 4.6, 4.7 are more advanced topics for conditional expectations, which we are just going to touch a little bit here. Okay, so let's start with section 4.1, which is called Radon-Nikodym theorem. And you may have seen all this already in your measure and integration theory course, depending on who gave that course. So if you've seen already what is the Radon-Nikodym theorem, then you can basically skip section 4.1 and 4.2. I still recommend that you look at the statement here and at the notation, just to get familiar with the notation and to remember what the statement was. If you have not seen Radon-Nikodym theorem, then I strongly recommend that you listen to at least section 4.1. Section 4.2 is only the proof. It's also interesting, and we need different tools like the Hahn decomposition of a signed measure and signed measures in general. So that's really interesting also from the measure theoretic point of view, but it will not be needed in the further course of probability theory. So what is the Radon-Nikodym theorem? We want to generalize the idea of continuous probability distributions. We call that distribution on the real numbers is called continuous with density p if the probability of the interval ab is given by the integral from a to b over the density p of x dx. And this holds for all a and b. Now we're going to connect this continuity idea to a completely different property, or seemingly different property. So that's what you see now in the second bullet point. There we define what nu is absolutely continuous with respect to mu means. And the definition is what you see there. So it says that for all measurable a, the mu measure of a equals 0 implies that the nu measure of a equals 0. Yeah, this is a property of mu and nu, and the Radon-Nikodym theorem now says that this property holds if and only if you can represent nu with respect, or as an integral with respect to mu. So nu of a is the integral of the relevant set A of the density p, which exists due to the statement of the theorem, with respect to mu. So this is the theorem, and the outline of this section is that we are going to carefully define what we mean by absolutely continuous, and we're going to carefully write down the statement, and then we'll give a lot of examples and deduce some elementary facts for these densities in particular, and the proof of this theorem will be given in section 4.2. We start the section with a theorem where we construct new measures with the help of a given measure and a density. So we start with a given measure space, and with a density, which is now just a measurable function from omega to the non-negative numbers. And then, as in the case of continuous probability measures, we're going to define a new measure by integrating the density with respect to the given measure over the set A. Yeah? And we do this for all measurable sets A. And the assertion is that this defines a measure on omega f. Let me remind you that you already know this construction from the case of continuous probability measures. In the case of continuous probability measures, the situation is as follows. So mu equals lambda, the Lebesgue measure. Yeah? So the reference measure, the given measure here is the Lebesgue measure. And we additionally demand that the integral of p equal 1. Yeah, the integral from minus infinity to plus infinity, p of x dx, is supposed to be 1 because we want our new measure to be a probability measure. Yeah? In this theorem 4.1, we do not need that. Yeah, we just state that the new thing is a measure, and in this continuous probability measure setup, we want the new measure to be a probability measure. Furthermore, you've seen this definition here, or this property, yeah, we called it a property there, for intervals from A to B. Yeah? Here we demand this to be correct for all measurable sets. Notice that on the real numbers with the Borel sets, it's sufficient to know the measure on intervals. So basically, it doesn't matter whether you demand this property for all measurable sets A or whether you just demand it for intervals. So I hope this helps you to see that the construction we want here in this theorem 4.1 is something that in principle you already know from this special case. The proof of this theorem is an exercise. So please check that the nu that we just defined here is indeed a measure on omega f. Let's take a look at my solution. So we have two things to show. The first thing is that nu of the empty set is 0, and the second thing is the sigma additivity of nu. So why is nu of the empty set 0? Well, of course, if you take the integral and you put the empty set here, then you basically integrate the indicator of the empty set, so you integrate 0, and this of course gives you 0. Now let's take a look at the sigma additivity, and for this we need disjoint sets, disjoint and measurable sets. So let AI be disjoint and measurable, and then nu of the union of the AI, I from 1 to infinity, equals, well, first of all, we use the definition, and the definition says that this is the integral over the union of the AI, p of x, d mu of x. And then we rewrite the integral with the help of the indicator function. So this is the integral over omega, indicator function, union of the AI, p d mu. Yeah, I leave out the arguments. And the indicator of the union of the AI is nothing else but the sum of the indicator functions of the AI. And this is because the AI are disjoint. And then p d mu. Yeah? And here I use that the AI are disjoint. And now I can exchange the sum and this integral because the things that I'm integrating here are non-negative. So this is Fubini's theorem that says that this is the same as the sum of the integral of the indicator function of the AI, p d mu. And now if you put back the AI into here, so I just erase the indicator and put the AI over here, and then I use the definition, then I see that this is nu of AI, and what we've shown is that the new measure of the union of the AI is the sum of the new measures of the AI, which is the sigma additivity of nu. And this shows that nu indeed is a measure. This was a warm-up, and we can now formulate the main theorem of this section, which is the Radon-Nikodym theorem. And roughly speaking, the Radon-Nikodym theorem says that the relation that we saw here in star between nu and mu, so that there is a function p such that nu can be represented with the help of the function p and the measure mu, this is equivalent to another property. So let's formulate this theorem. We are given mu and nu, sigma finite measures on some measurable space omega f. And the assertion is that there is a density p such that our relation star here holds if and only if another property, which I call plus, holds. And this property is as follows. For all measurable sets, if the mu measure of A is 0, then the nu measure of A is 0. Please note the difference to theorem 4.1. In 4.1, we are given a measure mu and a density p, and we define a measure nu. In the Radon-Nikodym theorem, we are given two measures, mu and nu, and they are in the relation star, so there is a density p, if and only if they satisfy this other property plus. As another comment, note that the property plus is seemingly easier than the property that is equivalent, the existence of a density. First of all, it's an existence theorem, and we will see in the proof that actually this direction is much more difficult because it's showing the existence of a function. And also the relation here that involves the density seems much more complicated, right? So for any set A, nu has to have this relation here with the density to mu. Instead, property plus only concerns the sets of measure 0. Yeah, so if you consider a mu 0 set, then it should be a nu 0 set. So the only thing that this property looks at are the sets of measure 0 of mu, nothing else. So of course it's ugly to call this property plus only. There are a lot of pluses in mathematics texts. So let's find a suitable name for this property here. And this is the following definition. So assume we have a measurable space and two measures mu and nu, and assume that plus holds. Then we say that nu is absolutely continuous with respect to mu. And we write it, nu is, well, less than mu. And this symbol here already tells us the direction. So if the mu measure is 0 of a set, then the nu measure should be 0. And note that this absolutely continuous resembles the star property. Recall what I told you about the continuous probability distributions and the correspondence to the property star. So I'll comment on this later on, but this is basically where the name comes from. Okay, so the rest of this section contains properties of the density P, so the density that exists whenever nu is absolutely continuous with respect to mu. And we're going to see a lot of examples. Contrary, the proof of this theorem is given in the next section, section 4.2. I was already talking about a density, and I didn't properly define this, so let's define what I mean by a density. Whenever we have that nu is absolutely continuous with respect to mu, then there is a function p such that nu of a equals the integral over a p of x d mu of x. This is the Radon-Nikodym theorem. And any such function is called a density of nu with respect to mu. We are going to see immediately, in fact 4.3, that the density is unique up to mu almost everywhere equivalence. So if you have two densities, P1 and P2, they are the same mu almost everywhere. We're going to use the following notation for the density. So we're going to write d nu by d mu. This is the notation for a function p. And we note that this symbol here is only mu almost everywhere defined, or defined up to mu almost everywhere equivalence. So this is the notation for the density. Let's continue with an example. So the example concerns the case that we already considered. If mu is the Lebesgue measure and the integral of the density equals 1, then nu is a probability measure, as you can check. You just have to plug in a equal omega, in order to show that nu of omega is 1. And if you put in omega here are the real numbers, and the integral over the real numbers p d lambda, so this integral equals 1. So indeed, nu is a probability measure in this case. So in this new notation, nu is absolutely continuous with respect to lambda being the Lebesgue measure, and the density of nu with respect to the Lebesgue measure, which is the density p. If you integrate that up, then you obtain 1. And this is if and only if mu is a continuous probability measure. That's what we called continuous probability measures. So I wrote this here as text. If lambda is Lebesgue measure, then what we called continuous distributions are actually, in the new notation, absolutely continuous probability measures with respect to the Lebesgue measure. Here is the next example, and this concerns the discrete probability measures on the real numbers. You may say, what? Discrete probability measures are somehow absolutely continuous? Yes. If you define the correct reference measure, then the discrete probability measures are absolutely continuous with respect to this reference measure. And the reference measure is the counting measure. So let mu be the counting measure, meaning that mu of the set with only one k in it equals 1 for all k, equal 0, 1, 2, and so on. And mu is 0 otherwise. And then what we called discrete distributions on n or n0 are in fact absolutely continuous distributions with respect to the counting measure, in the above sense. Let's consider the following example. So nu is basically the Bernoulli distribution. So 0 gets weight 1/2 and 1 also gets weight 1/2. And now if the mu measure of a set is 0, so if mu of A is 0, this means that there are no integers or non-negative integers in the set A, so that A intersected with n0 is empty. And if there are no non-negative integers in the set A, then also 0 and 1 are not in the set A. So this implies that 0 and 1 are not in A. And if 0 and 1 are not in A, then the new measure of this set is also 0. So this implies that the new measure of A is also 0. So we see that indeed nu is absolutely continuous with respect to mu. This suggests the following exercise. So we've just shown that nu, the Bernoulli distribution, is absolutely continuous with respect to mu, and mu is the counting measure on n. So by the Radon-Nikodym theorem, there is a density d nu by d mu, and you should compute what it is. Okay, so please stop the video here and try to solve this exercise. Here is my solution. So nu has mass at 0 and at 1, while mu has mass on all non-negative integers. And the mass of mu is 1 at the non-negative integers, this is this here. And the mass of nu at 0 and at 1 is 1/2. This means that we have to multiply the mass of mu by 1/2 at 0 and at 1, and we have to multiply by 0 at all the other places. So this shows that the density is 1/2 times the indicator function of the set 0, 1. So whenever you have 0 and 1, then you multiply the mass of mu by 1/2, and otherwise the density is 0. So much for this example. The next step will be to show this uniqueness that I already announced. So the density d nu by d mu is mu almost everywhere well defined, or it's unique up to mu almost everywhere equivalence. and this is the following fact. So if nu is absolutely continuous with respect to mu, then this density is mu almost everywhere unique. Let's prove this. Assume we have two densities, P1 and P2. And this chain of equalities here just says that P1 and P2 are both densities. For all A measurable, the integral of A P2 d mu is nu of A, and the same for P1. We're going to use this equality here for a specific set, namely for the set where P1 is greater P2. So for the set of all points in omega, such that P1 of omega is greater than P2 of omega. This is a measurable set because the functions P1 and P2 are assumed to be measurable. And if we plug this set in there and we rearrange this equation here, then we obtain that the integral of the indicator set of A, which for this specific A, note that I moved the A from here to the indicator function, of the difference between P1 and P2 is 0. This is the same as this equality here. Now clearly, since we are integrating over the set A, which says that P1 is greater than P2, this function here is non-negative. And if you integrate a non-negative function and you obtain 0, then you know from your integration theory course that the function has to be 0 almost everywhere, and almost everywhere is now with respect to this measure here. Now, by the definition of A, if x is in A, then P1 of x minus P2 of x is positive. So we can just cancel this term here, and this shows that this indicator has to be 0 mu almost everywhere. And what does it mean that this indicator function is 0 mu almost everywhere? Well, it means that mu of A is 0. So the mu measure of the set P1 greater than P2 is 0. And of course you can do precisely the same thing for the set A tilde, where P1 is less than P2. So you also obtain that the measure of the set P1 is less than P2 is 0. So the measure that P1 is not equal to P2 is 0, which means that P1 equals P2 mu almost everywhere, which is what we had to show. Here is the next exercise. Let's assume that nu is absolutely continuous with respect to mu. Now, please have a look at the left-hand side of the equality that we are supposed to show in this exercise. So there you see an integral of a function f with respect to the measure nu. If you compare this to the right-hand side of the equation, then there you have an integral with respect to the measure mu. And you don't only integrate f, but you integrate f multiplied by the density of nu with respect to mu. So you can imagine that you just cross out the d mu's that you see on the right-hand side. Imagine the two things that I circled red, they are just cancelled. Then basically this is a optical proof of the theorem, or of this exercise. Of course, you cannot go about this way, but well, you really have to prove something, and there's a hint written up here. So remember the construction of the integral. Start with indicator functions and then simple functions and so on. Okay, so please stop the video here and try to do this exercise. Let's take a look at my solution. So the hint was to remember the construction of the integral, and this construction started with indicator functions. So let's start with f being the indicator function of an a measurable. Then on the left-hand side, you get, well, f being the indicator function of a set, and you integrate this with respect to nu, so the left-hand side will give you a nu of a. What happens on the right-hand side? Well, of course, I also have to insert the indicator function of the set a here, and then what I get is the integral over the set a d nu by d mu of x d mu of x. And if we compare these two expressions, this is exactly the definition of the density, basically. Yeah? So nu of A equals this integral because, well, I plug in the density of d nu by d mu. Yeah? So these two things are indeed the same. Now, what happens if you take simple functions, yeah? Step functions? So what about f being simple functions? Well, simple functions are a sum of indicator functions. Yeah? So let's say it's the sum in I, alpha I, indicator function of the set AI. Yeah? And it's a finite sum. And now this equation here holds for indicator functions. So it also holds for linear combinations of indicator functions, yeah, because this sum can be put into the integral on both sides of the equation. So I wrote that linearity implies this equation here for the simple function f. And now I guess you know how to continue. So if f is a non-negative function, then f can be written as the limit of fn n tending to infinity, and the fn are simple functions. And we know that this equation holds for simple functions. Yeah, that's what we just proved. So the equation holds for the fn. And now if we take limits, well, this integral here is defined as the limit of the integrals of the step functions, yeah, of the simple functions. So this implies that the equation also holds for f. And the final step is if f is a general new integrable function, then what we are going to do is to split f into the positive part minus the negative part. And positive part and negative part are non-negative functions, so the equality here holds for f plus and it holds for f minus. So let me put a plus here and a minus here, yeah, meaning that for plus the equation holds and for minus the equation holds. And since f is assumed to be a general new integrable function, it means that the integral of f plus d nu is finite and the integral of f minus d nu is finite. And therefore the corresponding right-hand sides are also finite. And we can write the f integral as the integral of f plus minus the integral of f minus, and the same on the right-hand side. And this shows that the equation also has to hold for f. And we are done with this exercise. Here is another nice exercise. So assume that mu1 is absolutely continuous with respect to mu2, and mu2 is absolutely continuous with respect to mu3. The assertion of the exercise is that then mu1 is absolutely continuous with respect to mu3, and you have this nice formula for the densities. So the density of mu1 with respect to mu3 is given by the product of the densities of mu1 with respect to mu2 and mu2 with respect to mu3. So again, you have this optical proof by just cancelling the two terms that I circled red. And of course, this is not a proof. You really have to show that, well, these densities are equal. And yeah, I think that's a nice proof. So please stop the video here and try to do this computation. Here is my solution to this exercise. So of course, if mu1 is absolutely continuous with respect to mu2 and mu2 is absolutely continuous with respect to mu3, then, well, it's clear that mu1 is absolutely continuous with respect to mu3, because assume that mu3 of a set A is 0, then by this property here, mu2 of this set is 0, and then using this property, mu1 of this set is 0. Yeah, so this shows that indeed mu1 is absolutely continuous with respect to mu3. In particular, it shows that this object here exists. Now, how about the density formula? So what is mu1 of a set A? Well, we know that mu1 is absolutely continuous with respect to mu2. So we can write this as the integral of the set A, and we have to write here the density of mu1 with respect to mu2 and integrate this with respect to mu2. Now we want to use that mu2 is absolutely continuous with respect to mu3. And for this, we're going to use the last exercise. So we're going to write this here as a function f of x, Actually, we have to put the indicator of the set A here also. So let's imagine this is included in the function f. And then the last exercise says that if you integrate a function f with respect to mu2, and mu2 is absolutely continuous with respect to mu3, then this is the same as the integral of the function f. Yeah, and the function f here is now d mu1 by d mu2 of x times the indicator of the set A times now the density d mu2 d mu3 of x, and then integrated with respect to d mu3 of x. So this is exercise 4.4. And now we just have to interpret this in the right way. This thing here now is necessarily the density of mu1 with respect to mu3. Yeah, and this shows the formula. The next step is to talk about what happens if we have both relations. Nu is absolutely continuous with respect to mu, and mu is absolutely continuous with respect to nu. And in this case, we want to write that mu is equivalent to nu. Yeah, so this is this notation. So we say nu and mu are equivalent. Here is another exercise. So if mu is equivalent to nu, then there are two densities. The density of mu with respect to nu and the density of nu with respect to mu. And the exercise shows that they are in inverse relation. So the density of mu with respect to nu is 1 over the density of nu with respect to mu. That's what you have to show here. And of course, we are again not looking for an optical proof. We are just putting the things the other way around, but we look for the real proof. So please stop the video here and try to do this computation. Here is my solution. So what I'm going to do is to use exercise 4.5, and I'm going to put mu1 equal to mu, mu2 I'm going to put equal to nu, and mu3 I'm going to put equal to mu again. And then, since mu and nu are equivalent, we have that mu1 is absolutely continuous with respect to mu2, and mu2 is absolutely continuous with respect to mu3. And if I plug this into the formula that you see here in 4.5, then I obtain that d mu by d mu is the same as d mu by d nu times d nu by d mu. And this holds mu almost everywhere. Oh, almost everywhere. You know, I'm a probabilist, so I always write almost surely, but here we need almost everywhere. Now, what is d mu by d mu? Well, this is of course 1, or at least this is one possible density. You know, the constant 1 function is a possible density of d mu by d mu. And now we are tempted to just take this factor and multiply it to the other side, or divide by it, and then we obtain this equation that we want to have. However, we have to be very careful because this factor here could be 0. So what we have to ensure is that this is happening only on a set of mu measure 0. Yeah, if it's only on a set of mu measure 0, then it's fine. Yeah, outside this set, this factor here is positive, so I can just divide by it, and then I have this equation that I am supposed to show. So let's consider the set A of points where this factor here is 0. So where d nu by d mu of x equals 0. This is the problematic set where I cannot just divide by this factor. Yeah, for those x, I cannot divide by the factor because the factor is 0. Now let's compute the nu measure of this set A first. Nu of A, well, we use the density formula. So this is nothing else but the integral over the set A d nu by d mu d mu. And on this set A, the density is 0. Okay, so this integral here is 0, yeah, because, well, you integrate the 0 function on this set. But if the nu measure of A is 0, then by absolute continuity, the mu measure of A is also 0. And that's what we actually wanted, because, well, the set where things go wrong has mu measure 0. Okay, so indeed, mu almost everywhere, I can make this modification and take this factor here to the other side and obtain my formula that I was supposed to show in this exercise. Let's take a look at a few examples. The first example continues this theme of continuous distributions. Consider, for example, the exponential distribution. So I denoted this by PE. So the exponential distribution is characterized by this density here with respect to the Lebesgue measure. So far, we've always seen continuous distributions only on intervals, or we defined it as something that happens on intervals. So the exponential distribution applied to the interval from a to b was given by the integral from a to b over the density. And in the introductory course, and I looked it up, it was example 128 in the introductory course, we showed that knowing this probability measure on intervals is sufficient to know it on all Borel sets. So if we interpret this equation now correctly, then this here is the Lebesgue measure, and this is the density. Yeah? So this is dPe by d lambda. And this is what is written here. Now, the exponential distribution is absolutely continuous with respect to the Lebesgue measure. We just got to know the notion of measures being equivalent. So is also lambda absolutely continuous with respect to the exponential distribution? It's a question. If you want, stop the video and try to think about it yourself. So the answer is no. So one cannot obtain lambda from the exponential distribution because, for example, the exponential distribution applied to the set from -infinity to 0 is 0, but of course the Lebesgue measure of this set is not 0. This shows that the exponential distribution is not a reference measure for the Lebesgue measure, or technically correct, lambda is not absolutely continuous with respect to the exponential distribution. Because if it were, then the sets that have 0 measure under the exponential distribution would also have to have 0 measure under the Lebesgue measure, and this is not the case. Here's the next example, and as you can guess, this has to do with the counting measure. Consider the Poisson distribution with parameter r. So I denoted this by pp. P is not a parameter here, but P stands for Poisson distribution. And I chose the parameter r, not lambda, as it's usual for the Poisson distribution, because there's another lambda floating around on this page, which is the Lebesgue measure. And I didn't want you to confuse that. So the Poisson distribution is given by this formula here. The probability of the set with only the k in it is r to the k dividing k factorial times e to the minus r for k equals 0, 1, 2, and so on. And if we compare this to the counting measure, then indeed we see that the Poisson distribution is absolutely continuous with respect to the counting measure, and the density is given by these probability weights here. If you don't see this right away, then please stop the video and do the following computation. So the Poisson distribution of any set A is the same as the Poisson distribution of the set A intersected with the non-negative integers. And then you keep computing, and of course you use this formula here, and in the end you should end up with an integral of this density here, dpp by d mu, say of k, d mu of k. Okay, so as I said, if you don't see this right away, please do this computation, and then you check that this is indeed the density. Also here, one can ask whether the opposite absolute continuity holds. So whether mu is absolutely continuous with respect to the Poisson distribution. if you want, please stop the video and try to think about this yourself. And the answer is yes. And the density can be written down. It's just 1 over this density, which it has to be by the last exercise. And again, if you don't see this right away, please stop the video and do this computation. So compute mu of, say, a k, and try to compute this and represent it with the help of the Poisson distribution. And you will see that you need this factor here times the corresponding factor of the Poisson distribution, and that mu of all other numbers which are not the non-negative integers is 0. So indeed you can check that this is the right density of mu with respect to the Poisson distribution. Okay, so much for these examples. The next thing I want to do is to define another notion which is sort of perpendicular to the equivalence of two measures. This whole page is more or less informative, interesting hopefully, but rather informative, so we are not going to use this further in the probability theory course. So as I mentioned, the notion that we are going to define here is perpendicular to the notion of two measures being equivalent. And it's perpendicular in the double sense. So we are going to define when a measure mu is perpendicular to a measure nu. And this is as follows. So if there are sets A mu and A nu measurable, such that the union of these two sets is omega, so the whole set, and the intersection is empty, and the mu measure of the A nu set is 0, and the nu measure of the A mu set is 0, then we say that mu and nu are singular, and we write mu is perpendicular or singular to nu. So you have to imagine it this way. So this is omega, there's a set A mu, and if you take any set here from here, A, then the nu measure is 0 of this set. And if you take any set B from here, then the mu measure of this set is 0. Let's look at an example. So the prime example are the Lebesgue measure and the counting measure. You can have the following exercise here. So think of what are the corresponding sets A lambda in this case and A mu. Well, here is my solution. So A lambda, which is the set where the Lebesgue measure lives, is the real numbers without the non-negative integers. And A mu, which is the set where the mu measure, the counting measure, lives, is the set of non-negative integers. Clearly, these two sets are disjoint. The union is the set of real numbers, and the Lebesgue measure of this set here is 0, and the counting measure of this set here is 0. And this satisfies the conditions that you see in the definition, and this shows that the counting measure and the Lebesgue measure are singular. So I write here lambda lives on A lambda. Of course, lambda lives on the whole set, on the whole real numbers. But it doesn't matter if you take countably many numbers out of these real numbers, you still have a nice Lebesgue measure. The Lebesgue measure doesn't care about the non-negative integers. And similarly, the counting measure lives on n0. Of course, the counting measure lives on R also. So, of course, you can plug in whatever negative numbers into mu, but it will give you 0. Okay, so in this sense, mu lives on the non-negative integers. There's one additional and also just informative remark that I want to make here. So there's a so-called Lebesgue decomposition. So I refer to the book of Klenkes. And the statement here is as follows. So start with two arbitrary sigma finite measures mu and nu on the same measurable space. Then the assertion is that you can decompose the measure nu into two parts, nu1 and nu2. Nu1 is absolutely continuous with respect to mu, and nu2 is perpendicular to mu. So think of this as follows. So mu is your reference measure, and nu is the new measure in a sense. And this has two parts. One part that is sort of compatible with mu, that is absolutely continuous with respect to mu, and the other part is perpendicular, is singular with respect to mu. Think of the following example, and we had examples like this in the introductory course. So assume that you have a point mass at 0, which has mass 1/2, and then we have the uniform distribution on the interval 0, 1, which is nothing else but the Lebesgue measure restricted to the interval 0, 1, and this also gets a factor of 1/2. And then if you take as a reference measure the Lebesgue measure, then this part here, this is absolutely continuous with respect to the Lebesgue measure, obviously, and this part here is singular with respect to the Lebesgue measure. And if contrary, your reference measure is the counting measure, then this part here is absolutely continuous with respect to the counting measure, and this part here is singular with respect to the counting measure. So mu is the counting measure, and lambda is the Lebesgue measure. And in both cases you see that this is the decomposition, and this is called the Lebesgue decomposition. Maybe another notion, so this part mu1, which is absolutely continuous with respect to the reference measure, is called the absolutely continuous part of nu, and of course you have to say with respect to the reference measure. And the part nu2, which is this one here, this part is singular with respect to the reference measure, so it's called the singular part of nu with respect to the reference measure. As mentioned, the notions on this page are informative only. I still hope that they are instructive in sorting what is absolute continuity and in particular what are continuous and discrete distributions. I hope that this connects well to what you saw in the introductory course. This is the last exercise of this section, I promise. So I wrote down a whole zoo of distributions and measures. So Lebesgue measure, counting measure, exponential distribution, Poisson distribution, and whatever. And you are asked to sort these things according to whether they are absolutely continuous, equivalent, or singular to each other. So for example, if you have the line with the exponential distribution and you look at the column with the Poisson distribution, then okay, you ask yourself, is the exponential distribution absolutely continuous or equivalent or singular with respect to the respective other distribution or measure? Okay, so please stop the video and try to fill in this table. Notice that you have to fill in only half of the table basically, because the other half is sort of the other relation, so you just have to turn the symbols around basically. So here's my solution. I filled in the table. I'm not going to talk about all these items. Please just check with your own solution, and if you see things that are not the same, please think about it again. And if you have questions, please write to me or ask your tutor, and then we can clarify this. Let me summarize section 4.1. Here we looked at the property that a measure nu is absolutely continuous with respect to mu. This was that the mu measure of a set A equals 0 implies that the nu measure of this set is 0, and this should hold for all measurable sets A. The Radon-Nikodym theorem connects this property of absolute continuity to the existence of a density P such that nu of A for any set A, for any measurable set A, can be written as the integral of A over the density P with respect to the measure mu. And this density was then denoted by d nu by d mu, and we had a number of nice formulas for the for this density, which are all sort of such that you can see an optical proof by crossing out the d mu or d mu1 or something like that. And we proved all these things. What we didn't prove is the Radon-Nikodym theorem itself, and this will be the purpose of the next section, section 4.2.